Hello, today's lesson is on the laws of exponents. We've spent a fair amount of time talking about powers of 10, numbers written in scientific notation, and we're really getting ready to use those concepts. But before we do, we have to understand how exponential expressions behave when we multiply them, or divide them, or raise them to powers. And so that's what we're going to do today. Hopefully you have your guided student notes ready and your calculator handy. So let's begin. Scroll up here just a little bit. If we multiply expressions, exponential expressions that have the same base, right, we want to make sure that the base is the same, then what we want to do is add the exponents and keep the same base. The rule is that if you've got some base raised to the m power and exactly the same base raised to some other power, then the result still has the same base, but the powers have been added. It's a fairly easy rule to use. We should probably take a few minutes just to watch why the rule works. Because rule is really nothing more than somebody's way of writing down a pattern that they've noticed. So let's see what happens if we want to multiply 5 to the 4th power by 5 to the 3rd power. You already know that 5 to the 4th power means 5 times 5 times 5 again, and another factor of 5. And of course, 5 to the 3rd power, I'm going to color code this here, I'll use green for this one, is 5 times 5 times 5. So if we were multiplying 5 to the 4th power by 5 to the 3rd power, then we would have all of these blue 5s multiplied by these 3 green 5s. And it's pretty easy to see that when we get done, we're going to have 7 5s all multiplied together. And so that's 5 raised to the 7th power. And of course, all we had to do really was to look at the exponents. 4 plus 3 is equal to 7. And that's all there is to it. Everything else pretty much works in the same way, and when you're looking at the reading material that's posted online, you'll see a lot more detail about why this works all the time, not just with positive exponents, but it works if the exponents are negative, or if the one exponent is positive and one exponent is negative. It doesn't matter. The rule works. So 5 to the 4th times 5 to the 7th, 5 to the 3rd is 5 to the 7th power. And the sign of the exponents does not matter. The law applies for exponents of all sizes. Okay, so let's say we came down to look at example 2, and we wanted to see what the result of x to the 20th power multiplied by x to the negative 14th power would be. And if we follow the rule, then we will end up with the same base, which is x, and the new exponent will be 20 plus negative 14. Right? We just add the exponents together. And 20 plus negative 14 is 6. Take a second, pause the recording. You try letter B. If you were following the rule, then you kept the same base, and we added the exponents. So we need negative 5 plus a negative 3. And that whole answer is our new exponent. -5 plus -3 is -8. In some books, the authors ask you to rewrite things with positive exponents. I'm not exactly going to do that here, but you should know from our dealings with powers of 10 that the negative exponent, of course, means that all of these factors of 3 are in the denominator. So you could rewrite it as if we had positive exponents if you wanted to. We can also check this last one on our calculator. We want to make sure that the end result has the same value that our initial problem had. So the first thing we'd like to look at is 3 raised to the -8th power. That's what the calculator thinks it is. And then we would like to look at 3 raised to the -5 power. Don't forget to use that arrow key to come out of the exponent. Multiply by 3 raised to the -3rd power. And see what we have. And there we go. So we can check at least the ones that have a specific value for a base. Until we get familiar with the process, you should make sure that the value of your result matches the value of your beginning expression. All right, let's flip the page and see where we are from here. All right, so we've flipped the page, and that means the rule is covered up. But we know that in order to use the first law of exponents, the factors have to have the same base. Right? It was b to the m power multiplied by b to the n power, and we had the same base. So if we have something a little more complicated, like 5x to the 7th power y to the -10th power multiplied by 8x to the 3rd power times y, we're going to have to regroup this a little bit. We can put all of the coefficients together, 5 times 8. We can put all of the x powers together, x to the 7th multiplied by x to the 3rd. And we can put all of the y's together, y to the -10th power multiplied by y. And y has a 1 sitting right there, so don't think that there's not an exponent on it. But otherwise, we're just going to apply the rule. Of course, 5 times 8 is 40. X to the 7th multiplied by x to the 3rd gives us x, and the new power is going to be 7 plus 3, which is 10. And for the y's, the base is still y, but we have -10 plus 1 gives us -9. So our final answer is 40 x to the 10th power, y to the -9 power. And of course, if you wanted to, you could write this as 40 x to the 10th power, and you could drop all of those y's down into the denominator if you wanted. Now, if you do this, make sure that the exponent changes sign and becomes positive. All 9 factors of y are in the denominator. But really, that's about it. I can't make it any more complicated than that, unless we get another rule involved. So let's check the next one out. How do you divide expressions that have the same base? When we multiplied expressions with the same base, we had to add the exponents. So it probably won't surprise you that when you're dividing expressions that have the same base, we need to subtract the exponents. And just like we did before, let's take a second to watch what happens. If we had 6 squared divided by 6 to the 7th, we could write this as a fraction. And then, of course, we could expand all of this. So 6 squared is 6 times 6. 6 to the 7th is 6 times 6 times 6. And another 6. And then 3 more 6s. 1, 2, 3, 4, 5, 6. We need 1 more. There we go. So in expanded form, it would look like that. And I know, if I've trained you well, you just have this urge to find all the common factors that will divide out, which is great. You should do that. Well, there's just a 1 in the numerator. But what's sitting down here in the denominator? 5 factors of 6. In other words, 6 to the 5th power is in the denominator, which you know is exactly the same as 6 to the negative 5th power. Now I'm going to change colors here. If we used the rule, we would have said, I am dividing two expressions that have the same base. I will keep the same base and subtract the exponents. 2 minus 7, so we work the numerator exponent minus the denominator's exponent, and that gives us 6 to the negative 5th power. And of course that streamlines things for us. But here at least we can see why the subtraction happens. It's because common factors divide out. And just like we did before, we can certainly find that 6 to the 2nd power divided by 6 to the 7th power has a value, and 6 to the negative 5th power has the same value. So our answer and the original expression match. All right, we should probably finish this off real quick. This is 6 to the negative 5. We'll make sure your notes are complete. Just like we did before, the sign of the exponents does not matter. The second law, oh gosh, typo there. Let's cross out that word first. This is second. The second law of exponents applies no matter what. So it's time to try some. Let's flip the page and see what we can do. And just like before, I'll do the first one with you, and then you can try the second one on your own. So here we have two expressions with the same base. 7 is our base. They're being divided. So we're going to keep the same base. We need the numerator exponent, which is negative 9, and then subtract, and subtract the denominator exponent, which is 2. Hopefully your abilities to add and subtract positive negative numbers haven't deteriorated. Negative 9 minus 2 is negative 11. All right, your job, pause the recording, try letter B. Okay, let's see how you did here. Just like before, we're going to keep z as our base. We have the numerator exponent, which is negative 12. Subtract the denominator exponent, which is negative 15. You might remember that when you subtract a negative, it's the same as adding a positive. So we could look at this as negative 12 plus 15, which of course you know is positive 3. All right. Ooh, let's take a look at example number 6. That one looks really beastly, huh? Oh, but we didn't have a whole lot of room to do it, so maybe it's not as bad as it looks. What should we do and where should we start? Well, it's a fraction, and a fraction means we have to divide the numerator by the denominator, but I can't really divide by the denominator until I know what it's worth. So the numerator is simple enough, but let's clean up the denominator first. We'll just bring the numerator along. 6x to the minus 9. You know what? You focus on the denominator and clean it up, and then come back when you're done. All right, let's see how you did. 4 times 2 is certainly 8. That's not a problem. X to the 5th multiplied by x to the 20th. Since we are multiplying, we will add the exponents. 5 plus negative 20 is negative 15. How'd you do? Yeah? I hope it was good. All right, now for the next part. We have 6 over 8. That reduces. We have a common factor of 2 that will divide out. So we can turn that into 3 over 4, but that's about it for the constants right now. Let's look at the x part. Hang on a second, I'm going to make my fraction bar a little shorter here. There we go. There's the 6 over 8. Let's look at the x part. X is the same base, but we're dividing, so we need the numerator exponent minus the denominator exponent, which is negative 15. So we have negative 9 minus a negative 15. And just like before, that would be as if we had a negative 9 plus a 15, and that would give us a new exponent of positive 6. So you can write this in one of two ways. You can write it as 3/4 multiplied by x to the 6th power, or if you like keeping everything as a fraction, you can imagine that x to the 6th power as if it's being written over 1. And then it would look like this. X to the 6th would be in the numerator, and the 1 would multiply by the 4 and give you 4 in the denominator. So there's our second law of exponents working together with the first law. One more to go. What happens when you take an exponential expression and raise it to a power? And the third law of exponents says that if you have a power raised to a power, what we end up doing is multiplying the exponents. And remember, these laws are here because people noticed patterns, not because they were just making up crazy stuff. So it's pretty easy to show you why it is that this law should make some sense to us. Let's flip the page and try the next example. Here we have 7 to the 5th power, whole thing raised to the 3rd power. And of course, whenever you raise something to the 3rd power, you're multiplying it by itself 3 times. So if you had 7 to the 5th, let's just think about that as being one entity. And we're going to cube that thing. That means I have 7 to the 5th multiplied by 7 to the 5th multiplied by 7 to the 5th again. And now we're right back to where the first law of exponents took us. It said what we really need to do is add those exponents. So the new exponent is 5 plus 5 plus 5. And of course, nobody likes to write out plus, 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 especially when you're adding the same amount all the time. Instead, we just have 3 times 5, which is 15. So 7 to the 5th power cubed is 7 to the 15th power, and we can just apply that rule directly. Okay, so in example 8 and 9, we're just going to jump right to the things that look like they have a little meat to them, because multiplying exponents isn't hard. So let's see what's happening here. I've got a huge piece acting as the base, and then I'm going to cube that thing. So everything inside of the parentheses is being cubed. I would have 10 times x to the 8th times y to the 5th times 10 times x to the 8th times y to the 5th times 10 times x to the 8th times y to the 5th again. I would have that piece written down 3 times. And that means I would have 10 times 10 times 10, and we would have x to the 8th times x to the 8th times x to the 8th, and that would give us x to the 3 times 8, which is 24. And the y to the 5th times y to the 5th times y to the 5th would give us y to the 3 times 5, which is 15 power. And it looks like we're done here, but we're not quite, because we can do something with 10 to the 3rd. We know what that is. That's 1,000. But there's nothing more to do with the x's or the y's. So we have 1,000 x to the 24th, y to the 15th. Now over here in example B, or part B, we have a fraction that's being raised to a power. And that's the same. This fraction is being raised to the 4th power. If we were to write this all out, you'd see that fraction on paper in front of you being multiplied by itself 4 times. That means that you would have 3 times 3 times 3 times 3 in the numerator, which would give us 3 to the 4th. And you'd have x to the 5th times x to the 5th times x to the 5th times x to the 5th in the denominator, which would give us x to the 5 times 4, which is 20 power. And then just like before, all that's left to do is to take care of the constants. 3 to the 4th is 81. X to the 20th power in the denominator won't change. Okay, so yeah, I know, you know what's coming, don't you? Here we go, example 9. Looks like a beast, but you can handle this. I'm going to let you try this on your own here in just a second, but as a hint, start with the numerator up here. Figure out what happens to this piece, and then look at what happens to everything else. Pause the recording, come back when you're done. Okay, let's see how you did. In the numerator, we have powers that are being raised to powers, and that means we're just going to multiply the exponents. Don't forget that there's a little power of 1 right there by the a. So 6 has an exponent of -3 times 2, which is -6. A has an exponent of 1 times 2, which is 2. D has an exponent of 3 times 2, which is 6. And down below, we have 6 to the -6th power multiplied by d to the -3 power. Now I know that you just kept on writing from here, but what I want to do is to take a look at these pieces individually. Let's look at the constants. We have 6 to the -6th power divided by 6 to the -6th power. And though this looks a little bit weird, it's no different than 4 divided by 4. Some constant number divided by itself becomes 1. So these are common factors that divide out. Now nothing is going to happen with the a's because there's nothing besides a squared in the numerator sitting around there. But we can do some things with the d's. If we had d to the 6th divided by d to the -3, that would give us d, and the power would be 6, and we're dividing, so we need to subtract, and the power in the denominator is -3. So the new power on the d is 6 minus -3, and that's +9. So in the end, hopefully when you got done, you canceled those common factors, you kept the a squared, and the power on the d was +9. If you wanted to, you could have put a fraction bar here and put it over a 1, but dividing by 1 doesn't change anything. So our answer is right here. This whole thing is worth a squared multiplied by d to the 9th power. How'd you do? Hopefully not too bad. All right, so this was getting us ready for the work that's coming up when we start working with numbers that are in scientific notation. We already did a little bit of this in a previous lesson, but now we're going to be able to tell and anticipate the size of our answer. So let's see what we can do. This one really doesn't have any context to it. We just want to multiply these two numbers together. You'll remember the last time we did this, we made a big deal about keeping every number that's written in scientific notation together by using parentheses. We want to hold those two parts together. So we have 9 times 10 to the 7th multiplied by 5 times 10 to the 4th. And the parentheses are really important if we're working on the calculator. When we're working on paper, we can use that commutative law and rearrange the factors. So we have 9 times 5, and we also have 10 to the 7th times 10 to the 4th. You already know what 9 times 5 is. That's just 45. And now you have no problem knowing what 10 to the 7th multiplied by 10 to the 4th is. That's 10 to the 11th. All right, and we'll make that little dot an X. Our job was to write this result using scientific notation. And 45 times 10 to the 11th looks like it might be scientific notation, but it's not. The coefficient, remember that's the first number, has to be between 1 and 10. Remember, you're allowed to use 1, but you're not allowed to use 10. And of course, we can have any number in between. Right, 45 won't work. So how are we going to fix that? Well, what we're going to do is rewrite 45. You already know how to write a number in scientific notation. 45 is just 4.5 times 10 to the 1st. And then we'll bring this piece straight down. And again, you know what to do because you know how to deal with the product of two exponential expressions that have the same base. 4.5 can stay 10 to the 1st multiplied by 10 to the 11th. The base will be 10, and we need to add the exponents, which gives us 10 to the 12th. So there we go, 4.5 times 10 to the 12th. And of course we can check this, and we may as well. Let's see, 9 times 10 to the 7th power. Use that right arrow key to come out of the exponent, and then we'll multiply by 5 times 10, oops, not 11, 10 to the 4th power. Oh, drats. You should have said something. I know, I'm sitting here on a recording. You probably did say something. And of course I couldn't hear you. What's the problem here, right? For those of you who didn't see it, and we're just kind of going along with the flow, that exponent was negative. And that's going to change things a lot. So let's go back and see what that's going to do. We'll hang on to the calculator here in just a second. Sometimes these things happen and we have to adjust. So I'm going to use green so you can see where this is. So that is supposed to be a -4, which means we're going to come over here and make this one a -4. And then we'll take my eraser here. That exponent's not going to be 11 anymore. We need 7 plus a -4, which should be a 3. So this 11 isn't here. It's really a 3. Whoops, that's not a very good 3 even. There we go. But the rest is going to stay the same. We won't have an exponent of 12. Instead, we'll have 10 to the 1st times 10 to the 3rd. Adding exponents gives us 10 to the 4th. There we go. And of course, I never would have noticed that mistake because I was typing the same wrong inputs into my calculator. So there we go. Let's try that one more time. Close off those parentheses. I have no idea what that is. Oh, goodness. Ha, look at that. There's an 11 there. Let's try that one more time. I'm so flustered. Let's see. 9 times 10 raised to the 7th power multiplied by 5 times 10 raised to the -4th power. come out of the exponent, close the parentheses. There we go. That's better. Wow. Okay. So with that in mind, I think I'm going to take a little breather here. Let's slide down to the bottom one and see what you can do all on your own. Check with your calculator when you get done, and I'll catch up to you in a few seconds. All right, let's see how you did. So certainly voltage divided by amperage gives us resistance. So we have 6 times 10 to the third divided by 8 times 10 to the negative third. 6 divided by 8 is 3/4, which as a decimal is 0.75. What power of 10 should we have? Well, the numerator is 3, has a power of 3. Subtract the exponent from the denominator. So that means we're looking at 0.75 times 10 to the 6th power. And just like before, 0.75 is not going to work. All right, that coefficient needs to be between 1 and 10. So we'll rewrite that as 7.5 times 10 to the minus 1 power. And then we're multiplying by 10 to the 6th. Combine these powers of 10 over here, and we have 7.5 times 10. Negative 1 plus 6 is 5. So 7.5 times 10 to the 5th ohms. Now, do you really have to do all this by hand? No, probably not. I'm pretty sure you'll have your calculator around with you quite a bit. However, just like we did last time, if you leave off those parentheses when you're working your calculator, you're going to get some crazy result when you're dividing. You should already know, just by looking, that we have 3 minus a negative 3, that the answer is going to be something with an exponent that's 6 or something close to 6, because we might, of course, have to adjust when we get done. The exponent of 5 is reasonable. If you forgot your parentheses and you said 6 times 10 to the 3rd power divided by 8 times 10. Whoops. There I go again. This is not my best day, is it? Come out of the exponent, divided by 8 times 10 to the negative 3rd power. And you happen to forget the fact that scientific notation numbers are 2 pieces that need to be held together, and you didn't use those parentheses, the calculator will give you, 3/4. Because 3 plus negative 3 is 0, and there is no even power of 10 here. And of course, that is nowhere close to 7.5 times 10 to the 5th. If you felt like writing this out, you could. 7.5 times 10 to the 5th is 7. The decimal point has to move 5 spaces to the right, so we have to go past the 5, and then we'll need 4 zeros as placeholders. So that'd be like 750,000 ohms. So there we go. We want to use our brains in conjunction with the calculator. Be able to anticipate the size of your answer and make sure that you are using parentheses when you're entering numbers written in scientific notation. Your knowledge of the laws of exponents will help you catch an error or two if you make it on the calculator, because you'll be knowing what to expect. And with that in mind, I'm going to go for now, because it looks like my brain is leaving me. Have a really great day, and we'll talk to you in a little while. Bye-bye.